Hi, my name is Josh Willie, and in this video I'll be doing a derivation of a mass balance equation dealing with concentration of a solute in a system and how it changes in respect to time. So let's get into it. Alright, so first I'm going to draw out our initial, what we know basically. So we have let's say a container, some sort of cylinder. And in this cylinder, we have an initial height of water. Okay. So this initial height, we'll say, is equal to the variable, is equal to 1 meter. Now in this derivation, we're going to be mostly working with just variables, but when we go on to code this in MATLAB, we'll be doing, Python. We'll be coding this and actually using the actual variables and what they're equal to. But for this, we're just going to use the variables. So we are going to say that this is initial height of 1 meter, and this entire cylinder has a cross-sectional area. So this cross-sectional area is equal to 1 meter squared. Okay, and we can also say, another one of our knowns. Another one of the knowns is going to be that the initial concentration on the inside, so our concentration we'll say in terms of C. So for this, we're going to say it has a concentration of some solute within the water. So the solute, we're not going to be really worrying about what kind of solute it is. We'll say solute A has a certain concentration of C. At different points, it's going to be different. So the concentration coming in, which we'll go into in a second, is going to be different from the concentration of the system, and it'll be different at different points. So the concentration of solute A here is going to be equal to 0.1 kilograms per meter cubed. Okay? And we also know that there is going to be some amount, or say there's going to be a flow rate with a certain concentration of solute A coming into the tank. So it's going to be feeding into it. So let's go ahead and just bring this down here. So there's some sort of flow rate coming into it. We can say the flow rate was in terms of Q. So the Q in, or flow rate in, is equal to 1 kilogram cubed per second. Or no, it's not kilograms, sorry. 1 meter cubed per second. And has initial concentration, so our concentration of solute A coming in is going to be equal to, so C in is equal to 1 kilogram per meter cubed. So our inside of the system has a concentration of 0.1 kilograms per meter cubed, and our concentration coming in with a flow rate of 1 meter cubed per second has a concentration of solute A of 1 kilogram per meter cubed. Okay, and there is also going to be at the bottom here, let's say some hole. And this hole is going to let out a flow rate, so Q out, of alpha. Well, alpha will be equal to something. I'll go into that in a second. Alpha times the square root of the height, which is 1 meter, but like I said, we're going to leave it in terms of variables. So our alpha here is going to equal to 0.4. But our alpha also equals, our alpha stands for the area. So the area of the hole, the cross-section area of the hole that is letting out this flow rate, times the square root of 2 times gravitational constant. But this is not really important right now. We're going to be using this in the coding, our value of 0.4. But for right now, for the derivation purposes, we're going to leave it in terms of the alpha. Okay. So now that we have this, we can actually go into the mass balance portion of this. So we can start writing that out. So we're going to write this in terms of different points. So we have our mass of the system, is equal to the mass coming in times the mass, or minus the mass going out. Okay? So now we can start writing this. So we can also use a relationship. We can use a relationship which we know that mass is equal to density times volume. So we're trying to find mass. So we don't have initial masses, so we need to solve for mass. So we can say that the density, I'm blue so you guys can see it better. So the density of the system times, so volume in terms of this cylinder is equal to the area, or the cross-sectional area, times the height of the initial height of the water inside, which is 1. We're going to leave it in terms of variables. So for simpler, in the derivation problem here. So we're going to write this in terms of, so our volume is equal to cross-sectional area times our height. And we can say that our mass in is equal to the density coming in times the flow rate coming in. So let's erase this and make it clear. Yeah, so our flow rate coming in minus the density going out times our flow rate going out. All right, so one thing I forgot to mention at the beginning of this, in this particular problem, we are going to assume that our system is uniformly mixed. That means that everything has been stirred and everything's been ground down, so there's no really overall, we're going to assume that the densities in this case are approximately the same. So I'm going to make a note of that real quick. So a little note on the side here that we know that our density of the system is equal to approximately equal to the density coming in is approximately equal to the density going out. Since all these terms have a density, we can go ahead and actually cancel those out for make it simpler for us. So we can bring this out, bring out this density, and bring out this density. Okay. And now we're going to want to go ahead and do the derivative of this side and make it in terms of time. Since we're trying to find the concentration, where our end goal is to find the concentration over time and the mass over time. So we're going to do this, so the derivative of the top over with respect to time. Now here, we know that area, in this case, in this cylinder, particular cylinder, area will not change in the cylinder. It is not going to change, but the height itself can change. So we're going to say in this terms, A, our cross-sectional area, is a constant. So when you take a derivative of a constant, it actually comes out. It just stays the same. So we can go ahead and bring out, well, I'll go ahead and just change this. You can go ahead and bring out the area and say that our area times the derivative of height with respect to time is equal to our flow rate coming in minus our flow rate going out. And we can go ahead actually and substitute what our flow rate going out is. We know that our flow rate going out is equal to alpha times our square root of h, or height, the initial height of the tank. So we can say our alpha times square root of h, or height. All right, so we're almost done with our first equation. We're going to get 2 equations out of this whole process here. So we want to get this by itself, so we just go ahead and divide by this side by our cross-sectional area, and we have our first equation. So we go ahead and bring it over and get this by itself. So we know that our final or first equation is going to be our derivative of height with respect to time is equal to our flow rate going in minus our flow rate going out divided by our cross-sectional area. And that is our first equation we'll be using to code out in Python. So now that we've got that, we can actually go ahead and do our second equation. and we're going to look at the mass in terms of concentration of solute A at different points in the system. All right, so let's go ahead and just erase this. Okay, so now we want to go ahead and write, so our mass concentration of the system is equal to, this is kind of very similar, we're right in terms of very similar how we did this before. So our system is equal to the mass concentration coming in minus the mass concentration going out. Okay, so like before, we're going to say that the concentration of the system, which we know to be equal to C, we wrote it in terms of C, is, white in blue so it's easier for you guys to see again, is our concentration. So this concentration is going to take the place of our density like we did before. So, well, this time we're not going to cancel out. So our concentration of the system multiplied by, like I said before, our volume of the container is equal to the cross-sectional area times the initial height of the water inside. So our area times our height. And we're going to go ahead and just take the derivative of this. The derivative of all of this here with respect to time is equal to the mass concentration going in, which is equal to the concentration going in times the flow rate going in. All right. And then the mass concentration going out minus the mass concentration going out is equal to, so something we can see here is that when we're going here, the concentration is different when you're adding it in. So the concentration out here, like I said, is 1 kilogram per meter cubed. That's being added in. That is more than the concentration on the inside. So when this leaves, there's nothing being added, subtracted. So we can say that the concentration leaving at this flow rate is equal to the concentration of the system. So we are going to write so I'm going to write this relationship here. So we can say the concentration on the inside, which we said was equal to C, is actually equal to the concentration going out. They are one and the same. So I'm just going to keep writing this in terms of C for simpler so we can work with this. So this is a little relationship here. All right. So we can say the concentration times the flow rate going out, which we know to be alpha times the square root of h, or height. Okay, like we did before, we saw before that the cross-sectional area is a constant, so we can bring that out. And let's go ahead and do that. So at this point, we can go ahead and do product rule, and we are going to try and get, in this case, we are going to try to get, so before we have a derivative of height in terms of time, we're trying to get concentration by itself. So we're going to have to start doing a product rule and then get area over to the other side. We're going to get another derivative of height in terms of time and bring it over to the other side and get a derivative of concentration with the terms in respect to time by itself on this side. And those will be our two equations we use in Python. So the product rule of this is going to be, all right, let's say that let's go ahead and do this one first over here. So let's do the height comes out. So the first one, the height is going to be our constant. It's going to come out, and we can write this as derivative of concentration with respect to time plus this part of it. Concentration's our constant, so it's going to come out, and we will leave and do the derivative of height with respect to time. All right, so now we want to go ahead and, I can go ahead and bring these terms down. So this is equal to our C in Q in minus our concentration out times our flow rate out. So we're going to get this on the other side. So in order to do that, we're going to divide by this. So we're going to divide this term by our area. So that our area is gone on this side. And now we want to get our concentration by itself. So we're going to subtract this term and bring it over here. So we're going to do that. So then minus what we had over here. So we had concentration times derivative of height with respect to time. And now we're left with this. So in order to get our dc over dt by itself, we just divide our entire whole term over here by height, and we get it by itself. So our final equation is going to look like, over here, is going to look like our derivative of concentration with respect to time is equal to our concentration. I'm just basically rewriting this entire thing over here for simplicity. Concentration going in times our flow rate going in minus our concentration going out times our flow rate going out. This all is divided by our cross-section area, which we got over here. Subtract what we brought over from the right, left-hand side here. So our concentration times our, I'll go ahead and get rid of this so it's a little easier for you to see. Our derivative of height with respect to time. So you got this over here. And dividing this entire thing by our height. And this is our second and final equation, which we're using in Python or Google Collaboratory. And when we use this, and we will plot numerically these two equations over a time period of 100 seconds. All right, let's jump over to Python and get started on that. All right, so now we've got our equations for showing the initial the height and the also concentration of the solute. We are going to take those equations, we got those and drove those in the last video, and we are going to plot them using Python or Google Collaboratory, and we are going to plot them on a scale of 100 seconds. And we'll see how those look as they reach their steady states. So let's go ahead and start off by importing our numpy as np. We're going to do from scipy scipy.integrate import. We're going to import solve IVP. All right, we're going to do this from plotly.subplots import make subplots, and then import plotly.io as PIO, and then PIO dot templates underscore default equals plotly dark. So this will make our plots dark here. And hit enter. All right. Let's see if that runs. Okay, that runs. Sweet. So now we can go ahead and start putting in our variables, which we knew from our equations. So we're basically going to take the actual values from that our variables were equal to and plug them in here. We actually start solving and seeing them plotted out. So let's go ahead and actually comment this out and say that all of our values, so all mass values are in terms of kilograms, so our kg. All of our length values are in terms of meters. And all of our time values are in seconds. All right, so we've done that. So now we can go ahead and start putting in our values. So what do we know? We know that our area is equal to 1 cubic meter. We know that our height, our initial height, is equal to 1 meter. We know that our flow rate in is equal to, so let's say Qn is equal to 1. We know that our, we know that our concentration, our initial concentration of the water on the inside is equal to 0.1. We know our concentration coming in, our Cn, is equal to 1. And let's see, is that everything we need? We have our Qn, our concentration. Yeah. I think that's it. Oh, and we need our T. So we need our time variable. So T end is going to equal 100 seconds. All right, I think that's it. And if I need to come back and put anything else in here, I will do so. So now we are going to go ahead and write out our right-hand side function. So we need to find it first. So in order to define it, we need to define our right-hand side, what we're going to call it. And so first of all, the first variable that's going to come in here is our dependent or independent variable, which in this case is time. And we're going to give some other variable, a random variable, can be anything, is going to be equal to everything else, or what we're going to unpack. So our height and our concentration. So I want to say it's just equal to z. And we're going to start unpacking that. So I'm going to say that our height and our concentration are equal to said z value, not zip. And we're going to bring this down, and then we're going to say now that we can start writing our equations. So our first equation, our derivative of h, or small change in h, is equal to our Qn value minus, oh, that's something we forgot to put in here, our alpha. Our alpha is equal to 0.4. All right, I think we've got it now. So shift enter here. That's all called in. So Qn, so our flow rate in, minus our flow rate out, which is equal to alpha times our height times, well, and our height was the square root of height, so it's the same thing. Square root is the same thing as to the 1/2 power. So 0.5, and that was all divided by our cross-sectional area. All right, and all right. No, I don't know why it's giving me that error. So now that we've done that, we can go ahead and write out our second equation, which is our small change in our concentration, which is equal to our, our concentration in, so our C in, times our flow rate in. So let's go ahead and write that Qn. And then that minus our concentration. Let's see. Let's do our concentration on the inside. Since our concentration on the inside is equal to concentration on the outside, we can say our C of 0 or C value, I guess. And then we can do that times our flow rate out. So let's go ahead and say alpha times our height to the 0.5 power. All right, and this entire thing is divided by our cross-sectional area. And this all, we subtract concentration times our DH value, which we calculated before. And this entire equation is divided by our H. All right. So now that we've done that, we can go ahead and start returning our values. So let's go ahead and do that. Return. Return. So what are we returning first? Our right-hand side equation. And then next, let's return. So let's go ahead and put in our time values. So 0 to t end. And then next, we're going to do a numpy array. So numpy array. And that is going to be with its own quotation marks and then also brackets on the inside. So we're going to do this from, since we initiated, we did our height first and then our concentration. We need to make sure that we keep the same order. The order doesn't matter as long as we make sure we stick with the same order that we chose initially. So I decided to go return our height and then our concentration. So I'm going to go with H of 0 and then our C, our initial. So we've got that. All right. And then now I can do method equals redo. And then now we do dense output. Dense output equals true. All right, shift enter, let's see what happens. Okay, it gets mad at me. Dense output. There's an invalid syntax. Let's see. It's getting mad at me. Okay. Let's see. So, okay. So after looking at this for a second, I think I found the solution here. So this is not the way it should be here. This actually needs to be copied and brought down here below. So this is going to be brought in where, so a solve IVP. And then we're going to paste this here and bring this down here. So we can get rid of this. The return function needs to be in the defining of the right-hand side function. And we need to do a numpy array right here. So numpy.array, parentheses and a bracket inside for a numpy array. So then we need to do, as we called in first, we called in our height and then our concentration. So we're going to do our height function. So our small change in height function, and then our small change in concentration. Let's run that. Okay, sweet. All right, so now we got that. Now we come down here, and now that I've copy and pasted into the solve IVP problem, it should, let's run this. All right, that's good. And yeah, all right, sweet, it works. Okay, so from here, we can do our solution. And then it gives us our solution here. And let's set it equal to, let's suppress it and give it, set it equal to a value. So let's say our solution is equal to this. And we'll say that. We'll come down here and we'll start making a t-plot. So t-plot, our variable t-plot, is going to be equal to np.linspace. And our linspace parameters will be, well, it starts at 0, our time of 0 seconds, goes to tend, which is equal to 100 seconds. And then we're going to plot, let's say about 500 points, something like that. And then now, let's go ahead and, in the order that we did it, let's set our h, our height, and our concentration equal to our solution in terms of t-plot. Plot it over t-plot. Shift enter. All right, that works. All right, so we're on the home stretch now, so let's go ahead and plot this out. So let's set the variable figure, or fig, is equal to make subplot. Make subplots, and let's say our rows, number of rows is going to equal 1. And our number of columns is going to equal to 2. And now let's go down here and say fig dot add subplot, or scatter rather. And let's say our x parameter is going to be equal to t-plot. Our y parameter is, since we plotted that we've been working with our h first, we need to keep the same order. So we're going to do in terms of h. And okay. So now we're going to plot h, and then we'll go and do our rows now. So our number of rows, our row, we'll plot at row 1. And our column, we'll do it in column 1. Let's go down here and do a second plot, since we're doing 2 plots side by side, one for height and one for concentration. We'll do the second one as fig.add our scatter over the same x parameter. So x equals our t-plot. And this time, our y parameter is going to be our c, our concentration. We'll do it in row 1. And this time in column 2. All right, let's plot it out. Let's see what happens. Okay. So if we look at this here, this is our plot on the left here, our plot of our height as it reaches a steady state, or height of the water, and this is our plot of the concentration as it reaches a steady state. So this is over time of 100 seconds, and this is the amount of time it reaches the height, the amount of time that the height takes to reach its steady state, and the amount of time it takes our concentration to reach its steady state. And this is what we were looking for. Okay. Thank you so much for watching, and have a great day.